Hi, everyone. Welcome. Thank you so much for joining us here today. We are just letting some people in from the waiting room, so we'll give it a couple of seconds to let everyone come in and get settled. Thanks again for being here. If you want, you can drop us a note in the chat box there and let us know where you are tuning in from. We'll just give it one more minute or so. Okay, I think this sounds good. We'll go ahead and get started. So once again, welcome and thank you all for joining us for another Browsers 3000 learning session. Today, we are very excited to have Dmitry here to tell us about Fluence. Fluence is a peer-to-peer application platform that allows the creation of applications free of proprietary cloud providers or centralized APIs. Fluence's P2P platform provides a complementary compute layer to IPFS, enabling a wide variety of decentralized use cases. So Dmitry, thank you again for being here today, and we look forward to hearing all about Fluence.
Thank you. This is the learning session, and I want to get right to the point of adding value to the IPFS ecosystem from Fluence. And the entry point into Fluence is Aqua language. So I'm going to show you what is Aqua language, what it enables, and how it helps to compute, to add a compute layer and computations to IPFS with Aqua. So first of all, what is Aqua? Aqua is a programming language that programs network routing in open permissionless peer-to-peer networks. So instead of recompiling files, thinking about security every time and so on, you can write down the Aqua script, throw it to the network, and it will flow from peer-to-peer, calling functions on the way, getting data, providing data, and so on. So it's very easy to make peer-to-peer programs using Aqua. It's real, it's simple, it's powerful, and it's ready. It's ready to use. You can just take it and use. And I want to show you how easy it is with a tutorial example of browser-to-browser communication. Without IPFS yet, just the flow of peer-to-peer computation and how it could be expressed with Aqua. So let's think about delivering the message from one web browser to another web browser. What we want is to call some function that will trigger this sequence. As a web browser cannot be accessed from the outside and is limited in connectivity, it needs to connect to some node, which is called relay, to provide the services, the routing services for the browser. Then if we want to get to another browser, we need to get to another relay. And here's the flow. I want to call the function that goes to my relay, to the node that I'm connected to, then to another one, then to another browser, call some function there, and then get back to me with a response. That's how it could be expressed in Aqua. Here we have the snippet of Aqua code. So we have the notion of service, which has some functions which are executed outside of Aqua. In this case, inside the web browser. So we have the input type, the output type, pretty simple. And we have an Aqua function where we have arguments, and we say that on target peer ID, on the target browser ID, via target relay, we want to call this function, fetch the result, and provide this result back. So this via means that to get to the target browser and back, we need to get to go through this peer. So pretty simple. Let's take a look on the code and what it looks like in the code. So we have the examples repository, and in the intro folder, that's one hello world. Here we have Aqua, does the same code. And this Aqua gets compiled to TypeScript because we want to run it from the web browser. So this is the result of compilation of Aqua. We see the low-level code here. It doesn't matter. What matters is that finally, what we have after compiling the Aqua function to TypeScript is just an async function in TypeScript. Very convenient, that returns a promise of the result type. So let's see how it integrated. Here we have a very simple React application, and all we need to do to integrate our front end with this distributed workflow is just to import the compiled Aqua and import the function from it that we have just seen. Then we need to register the callback for the service that is called from the Aqua script. Here we just return hello from, like we are setting the state to have it displayed for the users. And we have the on-click action listener with a await, say hello, that actually triggers all this flow around the nodes. So again, to have this distributed workflow, all you need is to write around 10 lines or 7 lines of Aqua code, compile it, and import from the front end. So all you really need to do is to develop the front end. And I think it's awesome. Let's take a look on this example. So I have this intro running. I have 2 browsers side by side. And I have a list of relays of the Fluence nodes that I know. Let's pick one relay to one web browser, another relay to a second browser. Here we have the peer ID of this web browser and the node that is connected to. Let's copy and paste it. I'm copy pasting because it's the most simple way to go. But actually, in the real world applications, you can discover these peers, these IDs, and do algorithmic routing. So it just works. We have 2 nodes, we have 2 peers, and we just delivered the message, and it takes like minutes. So let's get to the presentation. Aqua is running in the Fluence network, and Fluence network is a very open were open one. So browsers can be peers in the Fluence network. They are treated just as peers. You can call functions on the browsers if they allow you to do it. They are just the parts of Aqua scripts. Nodes are also peers. They are running. They are built with Rust and running on some hardware somewhere, and they are capable to run WebAssembly computations bundled within services with the Marine runtime. So we have different peers like clients. It could be browsers or mobiles or anything. We have different nodes in the network, and we can have WebAssembly services on these nodes. What is interesting is that these services even can execute external effects. For example, they can work with IPFS files. You can instruct the WebAssembly service to download or to upload the file over IPFS, and that's what I'm going to show you. Or you can instruct it to fetch URLs, like get prices from an Ethereum node, or I don't know, the weather from somewhere, or fetch an image, or a webhook, trigger a webhook, something like that. So you can make quite complex workflows using WebAssembly and Aqua. But let's focus just on Aqua and just a bit of WebAssembly. The next part is about Fluence and IPFS integration. So first of all, I want to show how Fluence makes it possible to deploy WebAssembly, to deliver WebAssembly code from IPFS to Fluence node. So this finally means that you can point on the WebAssembly, on the computations, to link computations by CID. What's going to happen? From the browser, I want to ask the Fluence node using an Aqua script to deploy a WebAssembly package that is fetched from the IPFS node. The Fluence node will go to IPFS node and fetch this file by CID. IPFS node will download it and provide it to the file system. Then node will take this WebAssembly and move it to WebAssembly storage, and then it will compile it and run, and it will return the ID, which is callable, which you can just use for function calls. The service ID is different from this CID currently because it shows that this code is already deployed and it's ready to be called. So let's do it. I want to stop the first example and go to IPFS code execution example and start it. This is the fourth part of a tutorial. You can take a look on all the tutorials and readmes. They are more or less documented. And the structure is a bit more complex here because we have a service in Rust and Aqua scripts and front end. But finally, the logic is the same. So waiting for the front end to run is just TypeScript compiling. And while it's running, let's take a look on this. That's the API of the file that we are going to deploy and use. And here we have all the flow of deploying this service to the node using the CID of the services WebAssembly. So here we have the node where we want to deploy the service CID, the address of the node that hosts this service. Actually, we can get it from the node, but you can point on the node where you know it's cached or where you know that it's ready to serve you. And we have a callback to provide errors back to the client in case there's some. So it's running. Let's connect to some relay. And here it is. So I have already uploaded this file, process files, WebAssembly. I did it with IPFS desktop, actually. And here's the CID. And it's deployed. So it's deployed, I can remove it, and I have this service ID. So that's nice. Let's get back to the presentation. One step back about the Fluence plus IPFS integration. Is it tight or not? What's about nodes? So first of all, this integration comes by default. So the default deployment of the Fluence node contains IPFS daemon. So there is the Fluence node and the IPFS node as a sidecar by default. By the way, it's a question, what is a sidecar for what? Because you can think about the Fluence node as sidecar to IPFS. But finally, you can just use IPFS for storage. And if you're more about storage, then you can use Fluence for computations. Then there is a WebAssembly package that facades the IPFS node and the IPFS client for Aqua and for other services. This is required to ensure security, like to avoid RMRF or something like that. So all the IPFS related code resides here, and you can take a look at it, audit it, and then reuse it. And then all the services on the Fluence node can access files from the file system. You can fetch the file from IPFS, is on the file system then. And after that, you can use Aqua script to move the file from IPFS to the file system of the service, to the sandbox and back. So that's the next demo. I want to show how you can run computations on the data which is stored on IPFS. So it means that I want to apply the function coded on WebAssembly to the file which is addressed by IPFS CID. The flow is the following. I want to ask the Fluence node to apply a function to a CID. Fluence node will ask IPFS node to fetch this file. When this file is provided, it will be used as an input file. To be used, first it will be moved to the WebAssembly sandbox, as services and Fluence don't have access to the whole file system. This access is sandboxed, it's restricted, but you can move to the sandbox. Then the node will run computations on the file, and these computations will finally write another file with the results. Then the node will move this file with the results to IPFS node and ask it to upload it. To IPFS, it will return CID, and after that, the node will return CID to the browser. So let's take a look on how it works. Here we have the CID of some file, or is the same file that we just deployed. And we have a very simple function to get the size of the given file. Let's try it. So this file was downloaded, then moved to the service, then its size was calculated, and this number is uploaded as a file to the IPFS node. If you have time in the end, we'll try to upload different files and ensure that this hash corresponds to this content. Oh, I want to show the code perhaps, but actually it's pretty straightforward. We have this put the file and get put the file size function, and what it does, it goes to the relay, gets the file from IPFS. If it succeeds, then it processes the file size with the service. If it's okay, then it logs the file size with a coroutine, writes it to disk, and then uploads the file over IPFS, having the result. And finally, returns the result back to the client. So it's just the declarative description of what we want to achieve, actually. Looks quite straightforward to me. Actually, functions on the Fluence network are addressed by 3 parts. It's the peer ID, service ID, and function name. And you can have a service, a stateful service that, for example, backups itself into IPFS, or it could be a stateless service that provides several functions with like holding some invariant around the data that it modifies, or holding some access control credentials or something like this. But you can predefine this function name and say it's always, for example, apply. And you can predefine the peer ID or discover it over the network with some algorithm, like any peer that is registered as ready to serve me, something like that. And you can have the service ID by deploying the WebAssembly package by CID. So finally, you can have the function type of CID to CID, and the function itself can be expressed as the CID of the WebAssembly of the proper interface. So it's very flexible, but works awesome with IPFS. And it means that you can add computations to CIDs, to IPFS stored files really easily with WebAssembly and Fluence. And you can do, for example, IPLD mutations or backups to IPFS, or you can provide indexing of IPFS data and queries over IPFS data on Fluence, and so on. So if you want to try Aqua, the best way is to do it with a VS Code dev container. We have one on Fluence Lab/dev container. It provides syntax highlighting. We have the Aqua language plugin for VS Code. All the tooling is already installed, including the Aqua compiler and the WebAssembly compiler for Marine. And it contains many tutorials and examples, including those that I've just shown. And the Fluence network is up and running. It already has IPFS daemons, and you can run the node yourself if you want to, or you can use the nodes provided by the Fluence Labs. Speaking about Hackathon, we have some prizes. We have USD 1000 prize for the best overall Fluence submitted solution as judged by the panel. And we have USD 100 for using Aqua in the browser and integrating IPFS to create just any kind of decentralized application. And it's going to be unlimited in numbers. And for the details specific to Browser 3000 Hackathon, take a look on the dedicated repo, Fluence Labs / Browser 3000 Hackathon. And that's all. Here's the link to the Aqua compiler repo. We have documentation on fluence.dev, and we have Twitter, and we have Telegram. And probably we have also a room in Discord, hopefully, where we are open for the questions and we can provide the support. So that's it. If there are any questions, I'm ready to discuss them. And if not, I want to try to upload something else to the IPFS node. So this is the CID of the result. Oh, we can calculate the file size of the result as well. It's just 6 bytes. That's calculated. Just 1 byte. That's calculated. It's just the same. And here, that's the uploaded file. We can get it using IPFS desktop. So thank you for your attention. If any questions, I'm here. If not, please ping me on any chat or any channel. Thank you. There's a question about the hackathon participation with a huge application. And it's possible to use it during the hackathon.
Okay, great. Well, thank you again so much, Dmitry. There are links in the chat to find more information about the hackathon and also to get to the Discord channel. For any other questions, you can follow up with Dmitry there. Thank you again for joining us today, and we'll see you at the next one. Thanks, everyone.
Thank you.
Bye-bye.
Bye.